Hi, this is Danianju, your course instructor of Modern Physics 413. We are starting second article of your course outline, that is Wave Nature of Matter. Book that we are going to follow is Quantum Mechanics by Noida and Zetley. So this is the title page of the book that we are going to follow. You can easily download the book from the website b-ok.org. These are the topics included in this article. Section 1.3 include wave aspect of particles. It includes de Broglie's hypothesis, Davision-Germer experiment, Thomson experiment, matter waves for microscopic objects. Section 1.4, that is particles versus waves, classical view of particle versus waves, quantum view of particle versus waves, and wave-particle duality. Section 1.5, that is indeterministic nature of microphysical world. It includes Heisenberg's uncertainty principle and probabilistic interpretation. In wave aspect of particle physics, सबसे पहले हमारे पास concept है concept of matter waves, introduced by de Broglie in 1923, which is also known as de Broglie's hypothesis. Inspired by the duality idea, de Broglie gave his famous relation for the wavelength of wave associated with a matter particle that is also called as matter waves. Mathematically, we can deduce this relation by the famous Planck's relation, that is, energy transfer between radiation and material is discrete and in quantized form, which is h times f. This is the energy of a discrete packet, which we call photon. Now we require energy of a photon, which we can easily get from this total relativistic energy relation. As we know, by definition, light travels with a speed c, means there is no concept of static photon. That is, rest mass of the photon is always zero. So for the energy of photon, this first term goes zero and we end up with the second term. After cancelling the squares, we get the energy of photon equal to momentum times the speed of light, which we substitute here on the left hand side, and on the right hand side we substitute c over lambda for f. This relation we get from the formula of the speed of wave, that is v is equals to f lambda. After some simplifications, we get the relation for the momentum of a photon, which is Planck's constant by wavelength. Now, here this P is denoting the momentum. And we know that momentum is the characteristic of a particle. So it's purely a particle's property. And lambda is the characteristic of wave and is purely the characteristic of a wave. So this is the relation that we get. A particle's characteristic is related to the wave's characteristic in inverse manner. So this is not as much simple to interpret as it seems. Rearranging this, we get the relation vice versa. This is the de Broglie's wavelength of a wave associated to a matter particle of momentum p. At this point in quantum mechanical view, we consider a particle as a group of waves, or we can say these group of waves as a wave packet. Each group of waves is consist of waves with different wavelengths. But when we talk about the de Broglie wavelength, we are basically referring to that specific wave that is associated with that wave packet, which is the resultant wave of the superposition of all the individual waves present in the group of these waves. Now, the motion of this wave packet and the direction of the motion of this wave packet can be described by this wave vector k, which is given as the momentum vector by reduced Planck's constant. This reduced Planck's constant is equals to the Planck's constant by 2 pi. In order to derive this equation 2 from equation 1, you just have to divide both sides of this equation by 2 pi. Then on the left hand side, Planck's constant by 2 pi will become reduced Planck's constant, and on the left hand side, lambda over 2 pi will become 1 over k, that is reciprocal of the wave number k, which is described here, and the relation is given here. The concept of wave number is basically you have studied in your course of waves and oscillation in your second semester, but in order to refresh the idea, you may consult to any of the recommended textbook like HRK or University Physics, whichever suits you. But I am going to do a quick review here. So these are some conventional sketches of mechanical waves. The links are, you can check the further details with these links. In order to understand the concept of wave number, here we have a sketch of traveling wave that is completely described by this equation. Now, if you observe carefully, this equation has three variables. This equation has three variable parameters, that is y, t, and x, and the omega and k. These are some constant parameters. Means either we can sketch y versus x. Like in this graph, we have y displacement versus x distance, or we can sketch y versus t means y displacement and t time. Because we have three variables in this wave function. So the concept of omega angular frequency comes when you focus the sketch between y and t displacement and time. So what is this angular frequency or frequency of the wave? It is the number of oscillations covered in unit time. So if you carefully observe the time scale, you will find the unit time here in between 0 and 2. So in unit time, you can say the number of oscillation covered is 1 by 4th, because one oscillation is completed when a point on a wave repeats itself. So this point repeated itself here. So we can say that this is one complete oscillation. In this manner, in unit time, we have 0.25 oscillations per unit time. So this is our value of omega here in this sketch of the wave. For the concept of wave number, we will see the sketch of displacement versus distance, and according to the definition of the wave number, it is the number of oscillations completed or covered in unit distance. So if you see in this graph, this is also a y versus x graph. Here the unit 1 or unit displacement is this. So here you can see that number of oscillations covered are 1 and zero point 0.5. So 1.5 oscillations covered in unit distance. So this will be their wave number, the value of wave number. Or if you want to measure it in radian, then you can measure just like this half cycle will be measured as pi in radian. So from here to here it is pi, again 2 pi, then 3 pi. So here you can observe that instead of k there is 3 pi. The value of k is 3 pi mentioned here for this sketch of the wave. So I'm not going to account here the physics of mechanical waves. You can better learn it from the recommended text. Next, diffraction. Basically, it is a supportive topic because the conceptual understanding of XRD diffraction and Bragg's law is required in the division-jammer experiment. So, in simple wordings, diffraction is described as the bending of light around any obstacle. Just like we can see here, when the when the slit or the opening, so when the size of the slit is relatively larger than the order of the wavelength passing through it, no diffraction is observed here. The intensity profile that we obtained is just a uniform distribution, whereas when the slit's width is comparable to the order of the wavelength that passing through it, we observe these diffracted wavefronts, and the intensity profile that we obtained is no more like the uniform distribution. Now it is something like that. Here we can see in center we have the strongest peak of the intensity, and then intensity gradually decreasing on the both sides. So this is the profile of the intensity of the light that we obtain after diffraction. In double slit experiment, we observe the plane wavefronts coming from a single source of light splits and diffracted after passing through these two slits, and then they interfere with each other and produces a diffraction pattern on the screen, just like this. What is X-ray diffraction? Well, you can watch the whole video through this link. I found the topic very well explained via animated videos, but here we are going to drive the Bragg's law for the XR X-ray diffraction. So basically, X-ray diffraction is the scattering of X-rays through a crystalline material. The arrangement, the arrangement of atomic planes and interatomic spacing act as slits to produce diffraction pattern. The second thing is the wavelength of X-ray must be comparable. This wavelength of the X-ray must be comparable to the interatomic spacing of the material. So in order to get the true XRD pattern and to extract information of the material, let's focus this picture. So these are the atomic arrangement of the crystal, and since the single unit is repeating in the identical manner in all the directions, so they are forming a lattice plane inside the crystal. So here we have a different lattice plane. We can assume this first, and as we go deeper inside the crystal we have different lattice planes. You can take this as second, or this is as third lattice plane. What happens with the atom here is it absorbs the X-rays that incident on it. For some time it goes, for a little time it goes to the higher state and then returns to its ground state and emit the same wave with the same amplitude and same frequency The process is called elastic scattering. The incident wave, here we are considering that the incident wave is making an angle theta with the lattice plane. So keep in mind that this angle theta is not the incident angle. This is the angle that incident wave is making with the lattice plane. So the wave is scattered off with the same angle theta. Now, as we look at the second wave, since this wave have to go deeper inside the crystal, so it have to cover some extra path as compared to the first wave. Similarly, the third wave have to cover some extra path as compared to second wave. Remember, in order to get bright fringe on the screen, all the scattered waves must be in phase with each other so that they interfere constructively and we get a high intensity peak in our XRD graph. So, in order to keep second and third wave aligned with the first one, this path difference must be equal to the whole number of the wavelength. Okay, why whole number? Let's see here. One wavelength is actually the distance between two consecutive similar points on a wave. So from here to here, we have one complete wavelength. So alignment of these two waves won't get disturbed only if I displace this wave equal to the length of one wavelength or double of wavelength or triple so on. Okay, let's see what happens if I displace the wave to the one half of the wavelength. Okay, so we are comparing the wave 1 and wave 2. One complete wavelength is from point this to this. Here one complete wavelength is from point this to this. If I displace wave 2 to the half of the wavelength relative to the फर्स्ट, तो इस तरह से समझें कि हमें सेकेंड वेव को डिस्प्लेस करना है हाफ ऑफ द वेवलेंथ. तो अगर आप हाफ ऑफ द वेवलेंथ इस सेकेंड वेव को डिस्प्लेस करते हैं तो आपका ये जो क्रस्ट है ये डिस्प्लेस होके इस पॉइंट पे आ जाएगा. देन द क्रस्ट ऑफ द सेकेंड वेव will faces the trough of the first wave. जब आपकी वेव 1 और वेव 2 इन फेज हैं तो दोनों के क्रस्ट फेस कर रहे हैं, दोनों के ट्रफ फेस कर रहे हैं. लेकिन अगर आप हाफ ऑफ द वेवलेंथ से इसको डिस्प्लेस कर दें सेकेंड वेव को, तो फर्स्ट वेव का क्रस्ट होगा, सेकेंड वेव का ट्रफ होगा. बोथ ऑफ द वेव्स will be completely out of phase. They interfere destructively and we will get nothing on the screen. That is why it is important to have the part difference of a whole number of wavelength. So just like here we can see in wave 2 the half of the wavelength is covered by the incident beam and half of the wavelength is covered by the scattered beam. So in total we have a one wavelength of part difference of one wavelength. Similarly in third wave, one wavelength is covered by the one wavelength, extra path of the one wavelength is covered by the incident beam, and extra path of the one wavelength is covered by the scattered beam, and in total we have the part difference of 2 lambda. So that's why here all the scattered waves are in phase, they are aligned, so they are going to interfere constructively and we are going to obtain a high intensity peak on our screen. So all depends on incident angle. In experiment, for some angle there is destructive interference and for some angle there is constructive interference. So it is a kind of XRD pattern obtained from sodium chloride salt. So XRD means X-ray diffraction is a technique to investigate crystal structures in different materials, and various material properties can be studied through it. So here in this graph we can see that we have plotted intensity against y-axis and the diffraction angle theta, which is basically 2 theta, it is plotted against x-axis. So there are some specific angles where we get high intensity peak, and there are some range of angles where we are getting a very low intensity value. And here we can see that most of the scattered waves are destructively interfering here, and on the angles, these specific angles like this and this and this, here we are getting constructive interference of among the scattered waves. Bragg's diffraction is basically the diffraction that we observe when radiation within the wavelength comparable to atomic spacing is scattered. So Bragg's law is actually the condition that describes for the constructive interference to get the strongest peak. So this is the figure demonstrated earlier. So if we label the interatomic spacing as d, like from this atom to this atom, the distance between these two consecutive atoms in a lattice plane is d. Here is the angle labeled as theta. How does this theta come? I'm going to explain it in a few moments. Okay, so basically this angle theta is the same as that we described earlier, that theta was the angle between the incident wave and the lattice plane. So how can we assign this angle to this theta? We have to go to this slide again. Now, so we have assumed earlier that the angle between the incident wave and the lattice plane is theta. So if this angle is theta, then the angle between the scattered beam and the lattice plane is also theta. Now if we focus carefully, and from the theorem of a geometric theorem, that if a line is intersected by another line, then alternative angles are always equal. So if this line, is the which is basically representing the scattered beam, this is intersected this lattice plane. So the angle that is formed here between the scattered beam and lattice plane is the same as that here. Okay, now, and similarly we can say for this too, that if this angle is theta, then this will be theta also. Now what we are going to do, that since we Im we impose this condition that all these scattered waves should be in phase, so this line, which is represented by this black color, this and this is scattered beam, they are at the angle of 90 degrees, so they are perpendicular to each other, because ये बात हमने खुद से कही थी कि स्कैटर्ड वेव्स जो हैं वो इन फेज होने चाहिए। तो हमने वेव 1, वेव 2 और वेव 3 तीनों के वही सेम पॉइंट्स पिक किए थे और उन पे हमने लाइन ड्रॉ की थी। तो आपके पास ये लाइन और स्कैटर्ड बीम्स, जितनी भी स्कैटर्ड बीम्स हैं उनकी डायरेक्शनल लाइन जो है वो परपेंडिकुलर है। So basically this angle is 90 degree. If this angle is 90 degree, तो आप यहाँ पे we can apply complementary angles and we can say that this angle will be 90 minus 2 theta, cos theta plus theta, so this angle will be 2 theta, 90 minus 2 theta, and then again this line and this normal line, these are also perpendicular, so then again we can say that the angle, our required angle, which is this, the required angle, we want to find this required angle of the orange shaded triangle. So the angle we can write here 90 minus theta. ओके, सो सबसे पहले हम ये वाला एंगल सब्ट्रैक्ट करवाएंगे. Again we are applying the complementary angles, 90 minus theta and then minus this, so we left with this angle. After doing some mathematical simplification, you will end up with the theta, because 90 and 90 will cancel out and theta minus 2 theta will end. Okay, so 2 theta minus theta will end up with theta. So that's how we came up with theta here. So now it's clear that this angle will be the theta. Okay, now resolving this d into its component, we will get this line as d sine theta, because if you take this as your x-axis, or if you take this as your y-axis, then this d will be the projection of the d along x-axis will be d cos theta, and the projection of the d along y-axis will be your d sine theta. So if this line is d sine theta, this side will also be d sine theta. Okay, so we may consider this half of the part difference as L by 2. In the video clip that I copied from, they labeled this side as lambda by 2. But since we want to generalize it, we are not sure for the time being that it it may be lambda by 2 or it may not be lambda by 2. So we are generally labeling it as L by 2. Now this L could be lambda, or it can some other value. It can take some other value to the lambda, like it can be half lambda or 3 by 2 lambda. So in generalized form we are labeling it as lambda by 2. So coming up with the mathematics, considering the right angle triangle, we just did simple mathematics here. Perpendicular upon hypotenuse. Here, this is our perpendicular, and the hypotenuse side is D. So we label our perpendicular as L by 2, substituting here and over D. Now, the main point here is we have derived this relation that d sine theta is equals to L by 2. Now, since we have seen uh, in previous description that this part of the triangle d sine theta, this side is actually the half of the wavelength, is actually the half of the part difference, because the complete part difference will be this part difference covered by incident beam and the part difference covered by the scattered beam. So the total part difference would be L by 2 plus L by 2. If we are considering this part, then we have to take into account of this part 2. So adding both of them, you will end up with 2d sine theta, and imposing the condition of constructive interference that part difference must be the integral multiple of the wavelength. So our part difference is just 2d sine theta, which should be equal to integral multiple of wavelength lambda. So this is all about Bragg's law. It is just the condition for the constructive interference in Bragg's reflection or in XRD diffraction. This relation we will require in our next topic in division German experiment that we will do in our next lecture.